Caglayan. She is a postdoc at University of Pennsylvania in Dr. Nader Engin's group. She's been there since 2010. And before that, she got her PhD from Bilkent University in Turkey. And her research topic, her area is experimental and theoretical investigation of light-matter interactions at the nanoscale. So please.
Yep. Thank you very much for the introduction, Timsna. So I'm working on experimental and theoretical investigation of light-matter interaction at nanoscale. In my talk, you may heard lots of those words that I put here, like plasmonic, metamaterials, nanophotonics, nano-optics, nanoelectronics. But today, I like to focus with you on those four words: metamaterial, nano-circuit, plasmonic, and nano-photonic devices. And I'm going to talk about metamaterial-inspired optical nano-circuits, their applications, and plasmonics for nano-photonic devices. I'm Humeyra, and I'm from UPenn. Probably most of you heard about nanophotonics, what is nanotechnology. But let me just say that science of the light and matter interaction at the nanometer scale, we may call the scale around 1 micron to like 1 nanometer, and it covers lots of research areas. Nanotechnology goes from nanoelectronics to nanomedicine, nanophotonics from different areas. What I mostly investigate is that nanophotonics and also a little bit of nanoelectronics for nanoelectronic components. Light-matter interaction is the interaction of light and matter is defined by the laws of classical and quantum electrodynamics. And then when the light from the main source, sun, comes from a particle, hits for a particle, it will either scatter or it can absorb. It could be totally absorbed or partially absorbed, or it could reflect or transmit light. And then to define those properties, we define some parameters. Like, before that, this is a nanoparticle, electromagnetic hits a nanoparticle. It's a gold nanoparticle at 200 nanometer diameters. And when a light hits on it, it will scatter. It will mostly scatter, and it has a little bit of absorption. So the laws of the light-matter interaction and holds for this big-scale structures or also for nanoscale structures. And we defined those interaction with some parameters like permittivity, permeability, conductivity, chirality, susceptibility. And if we put the materials in the nature in a kind of this chart, we can find that very interesting properties. Nature provides us like many different variety of materials. Let's try to put them in this chart. For the first quadrant, which is permittivity is negative and permeability is positive, we can find lots of metals working below plasma frequency or some semiconductors. And if you go to the second part, where both of them is positive, it's fairly easy to find material. We can say most of the dielectric materials, like water, glass. In this part, where we have the negative permeability, this is the part where we get some ferrites working on this range. But for this part, it's not that easy to find some materials in the nature. And the idea of metamaterials comes here. The concept of metamaterials give us the options to design some materials and structures working in this regime, where both the permeability and permittivity are negative. And actually, the concept of metamaterial is not a very hard concept. It's fairly easy. When we have a host medium defined like those kind of blocks that I put there, and when we put some inclusions in it, those inclusions could be microscale, mesoscale, or nanoscale, depending on the interest of your wavelength. And then when you put those inclusions into your host medium, and then when you send an electromagnetic field to this medium, you will create either magnetic or electric dipoles at the position of those inclusions. And then you can define this medium as an effective medium, where you can define an effective permittivity and permeability. And then nature does this through the molecules. It's not a new concept. But we do this with the man-made inclusions. So it gives us lots of options to create the desired material, so to say. So, I mean, like there are lots of knobs that we can turn on and turn off. Like we can change the inclusions density. We can change the inclusion geometry, where we can put them, how we can put them, or we can change the host medium. So we can create a desired medium, effective medium. So far, since it starts with 2002 by Dr. Schring, is also one of the pioneers of this world. It started with a 2010 with a microscale device, microscale structure, like this one that you see in the top. And then many research done so far in the metamaterial area. One of the things that you may quickly see in this picture where I show like some kind of research that's many of them done other than this, but the inclusion in these mediums getting smaller and smaller, and this one, it's I think the smallest, which is in the nanoscale. I want to show you this graph. This is from a paper published like almost 2 years ago by Kostas Sakolis and Martin Wegener on Nature Photonics, that they very nicely review all the past achievements, so to say, that how we came to the nanoscale regime by changing all the inclusions, and then how we improved those metamaterial properties through the visible range. At this point, I think those are really nice structures. They're wonderful that we can create many different things out of those. But I think there's one word that my mom always used to say me, that if you have something nice, better use it for something useful. So when I look at around, the world is now as the microelectronic devices world. So when we look, I don't think we can imagine a day living without any microelectronic devices. And if you look at all those devices, the base thing is the circuit board that we can see. And when you look at those circuit boards, the basic elements of this board is RLC lumped circuit elements. The good thing with the RLC circuit elements that we always, I think, take them granted. We don't really pay attention on that. But the good thing is that once we define those elements, we don't have to go back and calculate what they really are. I mean, we don't really have to go back in the inside of it and then calculate what their property are. So we just get them, and then we put them, and we just need a voltage and current, and then we know what we need. And then we put them in a circuit element, and then we get our circuits. But when you look at those future nano devices, they're like, I'm sure you have seen them online that are like for example, even this like IBM picture that you see, that we don't see any of those kind of lump circuit elements. And the other thing is that you can find easily here that it's controlled with an input light. So I think here comes the question. So how we can create lump circuit elements, or if we can through the metamaterial structures. If we can replace those all LRC circuits in the nano optics, we can put them together like we did in the RF, and then create the circuits at the nanoscale, which we can control with the lights. This is introduced by 2005 by my great advisor Nader Engeda, and with his colleagues, that we can replace those kind of electronic lump circuits with some materials with different properties, which he calls Metatronics Area. When we have a material at the nanoscale object, and if this has a permittivity greater than 0, it will act as a capacitance. And if we have material which has less permittivity less than 0, it will act as an inductor. And the resistor comes for free because every material has some imaginary part which is like as a loss. And in this optical region, we define, now we are working with the displacement current, and then we define the impedance through the optical voltage over optical displacement. And I think this is wonderful that we can use those materials. If we now think ourselves as an RF designer, what would you do if with those elements? So we know that we have a circuit that we have to build, and we know the circuit formulas. Or we can go to book. I don't think we have the book anymore, but yeah. And then you get them and you put them together, and then luckily you get what you want with the characterization in the lab. And now if we go back to nanophotonics again, how would you design the nanocircuit? So we should have the circuit, and we should have some circuit formulas which is very similar to the, and then we're gonna put them together through nanofabrication. This time we need to put together through nanofabrication, and then we have to characterize them in our lab. And the other thing that with these circuits is that because now we control them through the light, with different light, they will act as a different circuit. So when we have this kind of structure where we combined basically L and C, and when we send the light with this polarization, it will be as an LC series circuit element, LC circuit. And for the other polarization, it will be a parallel circuit. So keeping all this in mind with this theory based on this, we defined we want to create an optical nanocircuit at near IR. So at near IR, the challenge is, I think it's easy to find, as I mentioned, to find a material which is permittivity greater than 0. But the biggest challenge is what is the material that we can use for the other part, for the negative part. So I replaced the air part. It could, with the air, it could be dielectric, but the air is for free and easy. And for the other part, we need some material which has plasmonic properties in near IR. And this is the design, which is the basic thing that you can build and easy to characterize. So this is the structures, nanorods that we defined to use. If we go back for the material search, recently transparent conducting oxides are one of the promising candidates to work on the near IR regime. This is a paper from a Purdue group, Alexander Boltasheva, that they showed that how transparent conducting oxides can be a good candidate to work in the near IR because they have fairly good low imaginary part and then good enough real negative part to work with. If you compare, for example, one of the transparent conductors, indium tin oxide, the imaginary part of the indium tin oxide around 2 micron is like 0.3, 0.8. Compared to silver, it's 5, so it's fairly low imaginary part to work with. So we decided to use indium tin oxide as our plasmonic material. It could be negative below 1.5 region. This is the Derrida model for the ITO dispersion. We also checked the properties of the ITO with the ellipsometry, so it's consistent with the fabrication, so we can use it in our modeling and simulation. So you can also clearly see in this one that it is getting negative. The real part of the permittivity is negative beginning from 1.3, 1.4 up to higher region. So what we want to do is we want to do nanorods that will act as an RLC circuits in the optic regime. So this is like a 2D nanocircuits. If you look at the displacement current, when we send this polarization, in this one, the electric fields in the plane of the nanorods, And the displacement current is changing, as you can see also in this graph here. So it will be, due to the displacement current, it will act like a TE, like a series combination of the circuit elements. And the other, so we can, since we know the impedances of all these elements, now we can go and write the impedance of the elements. We can use the basic capacitance and then write the impedance of the nanorod using the dispersion of the ITO. And then we also write the dispersion of the air region for the capacitance. And then since they are combined as a TE circuit, series circuit, we just add them so we can write the transmission out of it. This is like a kind of messy equation, but if you look at this equation and try to find out where is the resonance, where is the, so to say, like, because it's an RLC circuit, where is the resonance, where is the stop band of this? You can easily see that it only depends on the geometry. W and G are, the W is the width of the ITO nanorod, and G is the width of the air region. So it only depends on the geometry of the structures, and it also depends on the dispersion of the ITO, so the material. For the other polarization, it's very similar. So displacement current now changed. It's going through in plane. So we can only write them as a parallel circuits, and then we can use the same impedances and just put the equation of the impedances as a parallel case. And then we get the transmission, which is very similar, but the only thing that's different here that we change the ratio of the G and W. So you can get, if you look at basically where is the pass band, you can find using this formula. So it's great. So we put all the theoretical and the circuit theory, and we know what the base is. So we can go back and then fabricate our samples. And how did we do that? How did we do RTO nanorod fabrication? Is we used, and by the way, this is done with the collaboration of Sherry Kagan's group at UPenn. We used the nano-printing machine. This machine is, so say, first time used at Penn for this research. What we have is we have a glass substrate and we have an ITO. So we have some polymers to kind of duplicate the stamp on the structure. And then we use that stamp to duplicate the structure. Throughout this research, we used several stamps to get different kind of geometries, like changing the W and G, the width of the nanorod and gap of the air region. And then we use some nickel chrome deposit and liftoff, and then the etching part, so we can get the image of the stamp on our sample. This shows here the silicon master stamp, and also some imprinting results here, which works fine in a very large area. And this is the structure, ITO nanorod structures that we fabricate using the imprinting method. The good thing with the imprinting method is that in this research also we are interested on how large we can do those things, because we also like to see what will be the quality over the whole range. And then we are able to build this by 1 centimeter to 2 centimeter area. And in this case, in this sample that I show you, is the W is the width of the nanorods is 100 nanometer, and so the gap of the air region. And it's like a W over G ratio is like 1. And we did this several samples where we changed this W over G ratio from 1 to up to 4. So this is the characterization. For the characterization, so we use polarizer, so we can analyze two different polarization, and so we can analyze our circuits as a series or parallel combination. And we use the UV with near IR spectrum method for this analysis. And this is the results for the measurement where we change the W over G ratio. For the purple one, it is 1. W over G is 1. For the red, it goes to 4. So in this case, you will see this polarization where we have the series combination and the band stop. And this is for the other polarization where we obtain the band pass near IR filter. And I think it's amazing because it's only 100 nanometer thick of sample, and then you can still see how it's different, the stop band and pass band. And at this point, I like to compare this to the circuit theory calculations. Since we've done all the theory, we know how to calculate. So this is based on the circuit calculations that I'll show you. So again, we changed the W over G ratio from 1 to 4 for different polarization. At this point, we also checked how it works with the FDD simulations using a commercial software program, and this is the results. So it's not easy for you to compare all of them at this point, and let me put them in one slide. I'm going to show you all in one slide for only the series where we get the band stop, like the resonance. This shows for the circles, it shows the circuit theory calculations based on those equations. For the diamond one, it's the full wave simulations, and for the squares, it is the measurement. So you may also see here that our circuit theory calculations is also, although they follow the trend, they're different than they're a little bit different than the circuit measurement. I think the main one of the main reason for that is since in our circuit theory we thought that they act as a perfect capacitor, but we have lots of like befringing effects and everything, and also we have some losses and impurities coming from the fabrication. Although I think this really shows that when we go to the like a smaller structures, we can really get a better achievement, which is and it follows the trend. That's the good thing. At this point, as I mentioned you, so how we can change the impedances of those nano-circuit elements and how we can handle that. One of the things that I showed you that we can change the impedances through changing the geometry of the structure. And then the other thing that we can do is we can change the material itself. So we can change the impedances. At this point, up to this point, we are interested in the cross-section of changing the cross-sections. Now also, I'm going to show you some results that how we changed it, adding different materials. So for the first one, changing the capacitor, it was fairly easy because we can, instead of air, so far, we can just change it to a dielectric material. We have used those PBS nanocrystals. We use those crystals because they are nice, since we can squeeze them between the air gaps, and then when we wash them out, we will get the original sample. So that's why we like to use. And then let me show the data here. So this is how we obtain the shift through the red shift through adding those materials. And the other part is that changing the inductance value. Changing the inductance value, as you imagine, that was tricky because we need a material which could not be lossy, but it could give us enough shift to observe. For this one, we use just our structure where we have the nickel chrome on top of it. This nickel chrome is really, really thin, like 10 nanometers thin. So although they give us some loss, it's good. It's fairly good enough. So this is how we obtain the blue shift through changing the inductance value of those circuits. I think using those circuits, we can create the building blocks of the future devices. I mean, it's not just we use those nanorods, but we can do lots of different varieties. We can investigate different materials, like putting them on top of each other, like cascading, or we can even change the geometry of those structures, or we can further change the polarization and create many, many different varieties of circuits. I don't know if you have ever seen this one. This is called snap circuits for it's like a toy. But I really liked it when I saw it because it's really wonderful that you put them like They have like a project books. They give you those circuit elements. You put them, you snap them, and then you create many, many different circuits. And I sometimes feel like I have this in the lab, using those circuits elements. Up to this point, I show you the RLC circuit elements, but I think there was something missing with this. I think you may see better in these pictures what is missing. I haven't mentioned what is the cables that I can change. I can find the analogs of the RF to cables of this in the nano regime. I think that's also doable, and one of my friends is working on it. I'm going to talk about in this topic, in this talk today. We can use extreme parameter metamaterials like epsilon very large. This could be as a conductor, and then if we have an epsilon near 0, it could work as an insulator. So you can create your cables. Actually, my friend showed that this is really working very nicely using those kind of waveguides that will act as a cables where you change the shape, whatever, it doesn't matter. You will get this guiding anyway. But today I like to focus more on those epsilon near 0 materials or structures and how we can use this for plasmonic interactions, plasmonic devices, nanophotonic devices. So I mentioned to you that nature gives us lots of tremendous amount of materials. So do we have those in nature so we can use it? Or if we don't have, should we create them by ourselves? Actually, we are lucky that we have some. So for example, silicon carbide, around 10.3, 10.2 microns, it will act as an epsilon near 0 material. And also ITO, I just showed you that around 1.5 region, it will act as an epsilon near 0 material. So it's good news. But what will happen? Okay, that's great that we have those epsilon near 0 material, and I like to create those things. But what will really happen if we have epsilon near 0 material, right? Let's think that for a second that we have a time harmonic behavior with a convention of e to the minus omega t. Maybe you don't like it for the engineering. I think they use j omega t, but whatever. So when we look at the curl of H, we see that since epsilon is 0, so it should be 0. So this will give us that whatever the shape is, so the magnetic field inside it should be uniform. And the other advantage of this epsilon near 0 is that since we write the index of refraction using this formula, the index of refraction also should be n be 0, around 0, near 0. In this one, I tried to show that with a simulation that how E and Z difference than in glass or n equal to 1.5 material. Although there's lots of impedance mismatch, try to get in this E and Z structure, you can see that inside this E and Z, it's uniform compared to this other material that we have. So at this point, I'd like to show you what will be the advantages of using an E and Z material with a 2D scenario. In this 2D scenario, let's think that we have a perfect electric conductors, plates, and then we cut this in the middle and then replace it with a material that we can control, and then we covered it with a PEC, and then we can control this material. We can control the permittivity of this material. So let's think that if it will be an air, so what we can see is that since this channel, it's like 1/10 of the length of this channel, it will reflect most of the electric field. And we have very high reflection. And let's say that we turn the knob a little bit and then make it 0.5. You may see a little bit transmission coming out of it, but it's still really low. So let's turn it a little bit more and then get 0.1. In this 0.1, you can, at this point, clearly see that we have lots of transmission getting out of this channel and also less reflection. And just to see how it works, I made it really, really small. And then you can see now that it's almost a full transmission. Let's compare these two and focus on three good properties of these ENZ materials or structures. One thing is that reflection is really minimized. And then the other is that if you look at this channel throughout the length of the channel, the phase, because now we have a very high phase velocity, it will stay uniform throughout the channel. It doesn't matter what the length of the channel, it will stay uniform. Another thing is field is enhanced inside this channel because kind of you squeeze the field over there. So keeping all this in mind, I like to move and show you how it's going to work. So we like to, so far I always mentioned the ENZ materials that we can use through the nature. But so Metamaterial gives us lots of opportunity. Could we create one? Actually, yes. Actually, this has been shown that if you do get some thin layers of silver and silicon, then we can create a epsilon around zero structure. And also the other opportunity is using a waveguide that can operate around the cutoff, TE mode of the cutoff. Now, for this one, I like to talk a little bit about it. So if we have a wave propagating, so those are the propagating waves in the same medium, in the same frequency. And we can write the wave vector in the x direction of this. Like if we write it, it will be, we should change this constant. And if we compare the top one to the below one, it will be, the phase velocity is almost infinite for this one. And then for the waveguides, PEC rectangular waveguides, we usually define them like crossing plane waves in this waveguide. And if we get two modes, one of them is like top mode, and one of them is the propagating in the top, and then this one. And if we combine them, the intersection of this will be the solution of our waveguide, which is a propagating mode, and we can write it through those numbers. That we can define the index of our waveguide. The index of the waveguide is very similar to index of a material, where we define how the light propagates, how the electromagnetic field propagates along this waveguide medium. And since we can define the index, then we can define the permittivity of this waveguide, right? And this is the mode that we are looking for. So now we can write the permittivity of these modes. And then the good thing is we can control the modes using changing the width or the medium inside the waveguide, material inside the waveguide. Like for example, for these three kind of mediums, one of them is the propagating mode with this index. One of the mode is like a zero mode, epsilon is like N0 mode, and the other one is the evanescent mode, which is imaginary, and where we can write the permittivity using these equations, where we can define the permittivity of the mode of the waveguide. And this is the formulas that we used also for our rectangular waveguide. We changed you can either change the width, or we can also control it through the changing epsilon dielectric inside this waveguide. What we like to do is that we want to move forward and we want to create an ENZ waveguide functioning in the visible range. So for this one, this has been showed at MIM structures, metal dielectric metal waveguides. And for example, this is one of the structures has been done, and then they used zinc oxide using this, and then they showed that this is a theoretical calculation. But how we do this in using it, how we create an ENZ waveguide in the visible through our fabrication. Let me walk through to our fabrication and show you how we get this structure. So first, we used chrome, silver, silicon oxide E-beam evaporation, and then we cut using an FIB we cut a small, this kind of rectangular structure with different widths. Length is almost the same in all the samples. It's like 2 micron. And then we put another metal layer on top of it. And then it's 100 nanometer of silver. Again, we coated it with a very thin chrome. And then finally, we cut through the edge so we can get the light out of the waveguide structure. And I like to say that this work is done with collaboration with our home groups at AMOF. And so how do we put the source inside this waveguide is also a question that we use the catoluminescence system. This catoluminescence system has an E-beam coming through top. It's at like 30 kiloelectron watts electron beam. And when it comes through the structure, when it goes to metal, because of the metal transitions, it will create a source inside the ENZ medium. So that's all we want. We want a source inside this medium. So now we can investigate and we can gather it through the lenses and the color filtering and through the CCD. Let me show you the data that we get. This is a waveguide with a width of 250 nanometers. In this one, we scanned the structure, changing the wavelength in the center of the electron beam. So we changed the position of the source coming from the top along this length of the structure. So in this one, you can see this plasmonic modes, propagating plasmonic modes, and this is a calculations that we done to compare the experiment. And so in this one, since we like to operate around the TE mode cutoff, so we can get the epsilon near zero waveguide. So we shrink the waveguide a little bit, change the waveguide width to 180 nanometers, and now we can clearly see the cutoff of the TE mode at around 700 nanometer wavelength. So this also shows the scan over the center of the with 5 nanometer steps for different wavelengths. So I want to show you for different waveguides with different widths. This is for 400 nanometer waveguide, and this one is 190 nanometers. So you can clearly see that for this one, inside the ENZ, the edges a little bit, because they're like in cavity enhanced, because of the air region and the metal region. But if you look at the middle region especially, the electric field stays uniform compared to other waveguides. So it will act as an ENZ waveguide. And this is the calculations that we showed here. This is the dispersion calculation of the waveguides. All the colored graphics here, all the colored dots, corresponds to measurement. Through the measurement, we obtain this plasmonics and then count the plasmonic modes and then get the dispersion. And the gray ones are the calculated ones. So you can see that they really they have a really nice agreement here. And this has been published recently and get some attention from the community. So what I like to go is now in this part of the talk, I showed you how my experimental works mostly, and then also some modeling. In this part of the talk, there will be only theoretical calculations and how we use ENZ to control the coherence using emitters inside it. So far, we put the dipoles inside the ENZ, and then we show that it's really working as an ENZ medium, and it's really nice that we keep the field same, uniform, and get it. But ENZ could be useful because of it locks the phase through the entire medium, could be useful for many other things. We can either control the coherence of the emitters inside the ENZ, or the other thing is we can enhance the optical radiation. Today, my work is only so far as coherence of the emitters, so I'm going to only show you this, but this is also possible. We can also get enhancement. Controlling the coherence, let me tell you a little bit about this, what I mean about this. So when we have an electromagnetic wave, incident on multiple scatterers, or you can think them as sources inside the medium. And then they may have some degree of coherence. So what would you do usually for the conventional medium, in order to reduce the decoherence? Either we put them together so the separation will not be really high. So this is like a light, and then we have some decoherence on the light, and then so we have two particles throughout this light interacting, and then we want them to be coherent, so we want to put them together so they are not effective from that coherence that much. And the other thing that we can change the wavelength. So if there's if we have a scatterers, and then if we have let's say a coherent light, and we have a small oscillation in the position of those scatterers, now we want to decrease the wavelength, so it will be electrically, length of the position of the uncertainty will be reduced by increasing the wavelength. So basically, you want to be less affected from all these oscillations and the sort of the coherence of the medium and also the position of the sources. As I mentioned in my talk, that for the ENZ structure, when we have the index around 0, it will stretch the wavelength. So when we stretch the wavelength, so it means that although you have a electrically defined lengths like D, now inside the ENZ medium, because of the effective wavelength is stretched, compared to the wavelength, it's getting very small, although you keep it the same. So how we can use it? To show the proof of principle, I'm going to show you how we can do it in the coherence in a 1D system. Let's say we have a source, we have a plane wave source, and then we have some bit of oscillation in the source, in the position of the source, and we are changing the index of the medium. So we're going to check we have an observation point, and we will look at the electric field and how the decoherence is changing. So this part is, just bear with me with one slide that has some equations in it, we define the electric field coming from this source through this equation. We input the source position as a ZST there. And then to calculate the coherence, we calculate the autocorrelation function of the electric field. And then we look at the absolute value of this autocorrelation function. This autocorrelation function gives you the measurement of the sharpness of the interference patterns. So it will give you the idea of the coherence, how it's coherent or not coherent, basically. And we define the randomness of this source using a Gaussian distribution. So we can define the RMS value and also the correlation time through this. For example, if we have a function like this, if we have a source that has some oscillations in its position, like we define in this one. We have shown the Z over lambda, and this is through the time. And when we look at the autocorrelation of this, by changing the index of the medium, we can see that orange is for the 1 when we have in the air. And then when we change the index a little bit closer to the 0, it will get a perfect coherence like 1. And then when we look at this other case, which is a very similar, I just changed the parameter from parameter of the source oscillation, we will have a similar graph, similar data. So changing the medium definitely changed the coherence, so we can use ENZ mediums to get a correlated emitters. To make it in a 2D scenario, this is a simulation where we use the 2-dimensional structure. It's a 2-dimensional cylinder, and we have dipoles in it. Those dipoles is separated by 2 lambda. Here I picked the wavelength as 2 micron, and then those dipoles have an oscillation in their position defined using a Gaussian distribution as well. And then this is when we have those sources in air. And then if you look from outside, like let's say that we are like far from those, like 10 lambda wavelength away from those cells, and then just looking for the electric field, we can definitely see the oscillation on those sources, positions. But let's put them inside an ENZ medium. So this picture clearly shows that when we put them inside an ENZ medium and when we go far and look at them, we don't see the effect of this oscillations of the emitters. So in the ENZ medium, it doesn't matter where you put the dipole anymore. It could be anywhere. It could have oscillations, but you will have the same electric field. They will be all coherent, so to say. To put them in the numbers and graphs, I'm going to show you the electric field that we gather 10 lambda wavelength away from the sources and then compare it to the ENZ. In this red one, it is ENZ, and the black one is air. This is where we have only two dipoles, and we plot the imaginary and real part of the electric field. And this is the standard. In this one, the standard deviation of the standard deviation in the position of the dipoles is lambda over 8, and in this one it's lambda over 20, which clearly shows in both cases that the ENZ give us a more coherent emitter sources. In this one, we changed the electric fields. We calculate the electric field for, instead of 2 dipoles, we changed to the 5 dipoles, and we can still observe the same nice effect in this one. In here, in this slide, I put all together, everything all together. Here in this part, we have the different kind of standard deviation values of the sources, and where we get the normalized standard deviation compared to the ENZ compared to the air. And in this one, we change the dipole of the number of the dipoles, and then we can still observe that the standard deviation of the electric field is very low compared to the air region. So with this, I want to conclude that I showed you how we can create some nanocircuit structures using ITO nanorods, how they will act as a nanocircuit element in the optical regime. And I showed you our near IR filters. And I introduced you the ENZ waveguide, which will give you the opportunity to fix the electric field magnitude and phase through this waveguide, and then let us waveguide and manipulate light through these ENZ structures in the optical region. And then the other thing that I discussed today is that what will happen when we put emitters in this ENZ medium, and then how it will help us to change the coherence in these emitters. And with this, I'd like to thank my collaborators, Nader Engeda and his group, especially Dr. Brian Edwards and Uday Chatter, and also Sherry Kagan group at Penn, and Dr. Sanghun, her postdoc, and Murray group, who will generously give us those nanocrystals at UPenn, and also Albert Pullman and his group for using his facilities and working with us. And thank you for your attention and then having me here.
Any questions?
What are the requirements to get an epsilon or zero material?
I think you can, like for most of the materials, all of the materials around the plasma frequency, they will have epsilon near 0. But the critical point is that although they have this epsilon near 0, will the imaginary part low enough to work with? So yeah, for example, for silver, for gold, yes, in the plasma frequency, I think for the gold, it will be like 400 nanometers. You will have the epsilon near 0, but if you look at the imaginary part, it's not, I mean, it's workable, but yeah, still give you some headache.
So
yeah.
what materials would you recommend?
I mean, it depends on, I think, the wavelength. For the wavelength of this near IR, I will work with the ITO. Indium tin oxide is really good. Or recently, AZO, aluminum doped zinc oxide, or gallium doped zinc oxide is really good. And for the visible, I would recommend recently published some papers that titanium nitride, TIN, instead of gold, that works. That has a real part negative enough, but less than, the imaginary part is less than gold. I think I would recommend that.
Thank you.
Oops.
Any other questions?
If you could go back to the coherence of the resistors.
Yeah.
Can you show the signal?
Like here, like
Still back. Back.
this one.
Yeah.
Yeah.
So the source, the plot to the left, there, top left.
Yeah.
The source trend is varying with respect to time there, right?
Yeah, this is how the source position changing compared to the wavelength
So
through
you
this.
have to choose a particular function to do that.
Yeah, that's what we choose like I mentioned, I think here, we define it as using a Gaussian function,
Okay.
which we can control the RMS value and standard deviation value. So
But
we
if,
change.
if that function was truly random, then no matter what you do, it's all zero, right? If you could,
Here, you
Yeah.
mean this
No.
one?
yeah.
I think, I think, I mean, if you would add randomness in somehow, like you will see, I mean, that kind of oscillation in the source. So, I mean, I think that this point is that, I think it doesn't matter if we have a Gaussian distribution or other distribution here. The point is that if we have some randomness in the location of the source, we will somehow see the effect of it. So the correlation function would not give us 1. It will
So
be
zero if it's
yeah.
random.
Oh yeah, you mean that? Yeah.
So you have
It will be around 0.
So the way the source is moving with respect to time should be a particular function to get a autocorrelation close to 1.
Oh no, I think here how we get through the 1 is by changing the index of the medium. Here, here the index of, so we have an index of, this source is in a medium, index of n. And we change this n from 1, like air, to 0. And then when we change this one, also it comes from here through this, here, up here, like here, it comes through here, n, index of medium. And then when you use this, when we calculate it, this is for the index of medium 1. So when it is 0, you will get 1. And when it's not 0, you will have oscillation because it's oscillating. And when you make the index of medium different, you will have the perfect, like a 1 degree of coherence. So degree of coherence usually defined it when you have around 0, basically it's decoherent. When you have 1, it is coherent.
Do you see ENZ material as a way of generating coherent source of near-infrared radiation?
Yeah, actually, I do. Yeah, yeah.
Project some numbers for us. What kind of powers and what kind of source?
Oh, like
you
this
use
is.
that to make coherent them?
I don't have the numbers, but I think I will envision that if we can put like some quantum emitters which has their own like randomness in their position, then we can look at how the radiation, so we can
They will
observe.
all come together
Yeah,
as a coherent
yeah,
source.
that will create a coherent source. Yeah.
Okay, so what's bothering me about those autocorrelation curves is that central peak.
Yeah.
I would expect naively it would just get broader. and
Yeah,
then
that's
flatten
what.
out. So why doesn't it do that?
Yeah, that's what I expect when I started this one. But I think maybe if you play with, when I play with those, you see those RMS value and the correlation time value. I think when you play with them a little bit, this thing, this orange peak, it gets broadened, and then, but still, it will keep the same, so to say, the broadening, and then it will become 1. I mean, those numbers are not magic. I just picked them. But yeah, if you play with those numbers, I mean, you can get that kind of effect.
Any last questions? Okay, thank you very much.
Okay.